Okay. I'll wait just a couple of this little bit, see if I'm going to get anybody to join. Okay. We can get a couple more. Get a couple people in here. So my plan for this session is to do sections 4.1 through 4.3, and then do 4.4 and 4.5 on Wednesday, and then do one more session on Friday. Again, I am uploading all of these to YouTube after we get done with them, and then I'm providing the links in Canvas for you guys. So for anybody who's unable to join for the Zoom session, you do still have access to the videos. I'm trying to do, try and make this as somewhat close to instruction time as we can. I know that there is the distinct possibility now that we may get shorted another week on instruction because of Smith County or the city of Tyler, I should say the city of Tyler, doing the stay-at-home order. So, we'll kind of see where that goes and when TJC is going to opt to do the come back into session. I am still planning to do test 3 and test 4, and then the final exam in class in the physical classroom setup. But if that's not going to be an option, then I will figure out what we are going to do, and I will make sure to communicate that via Canvas. I will probably also use a couple other platforms, maybe my math lab, a couple of different platforms to try and make sure that you guys are getting that information type of thing so that you know. So I'm going to go ahead and get started so that we can get this done. So I'm going to switch to my whiteboard here. So starting off with section 4.1, this is exponential functions. So exponential functions are in the format, okay, b to the x, okay. The difference here is beforehand, when we were doing things like this, we were changing the number down here, but I was always cubing the number, okay, and going through. So I would do 2 cubed and 3 cubed, and I could do 1.7 cubed and things like that. What we're doing now is we're going to lock a number down for our base, and then we are going to run through all of its powers. So now, if I did something like 2 to the x, I would be looking at 2 squared, 2 cubed, 2 to the 4th, 2 to the 1.5, or 2, so things like that, where we are now changing what that exponent is. Now, a couple of things. Your base has to be positive. Okay, so it must be positive. And this is because if we pick something, say like -2, if we do -2 to the first, that's -2. -2 squared is +4. -2 cubed is -8. We are ping-ponging back and forth between negative answers and positive answers. If I go one more, I'm back over at 16. We are ping-ponging back and forth between positive answers and negative answers, and we're not allowed to do that, okay? So B has to be positive. The other thing is B can't be 1, because 1 squared is 1 and 1 cubed is 1 and 1 to the anything is 1. So it gets really, really boring doing any of that, okay? So these are our trinomials. Now x, the exponent up here, can be anything it wants to be, okay? So that is kind of up in the air. It's anything that you want it to be. Now then, they give us an example. We have f of x equals 42.2 times 1.56 raised to the x, okay? And they say that this models the average amount spent in dollars at a shopping mall after X hours. And so they want us to figure out, to the nearest dollar, the average amount spent after 3 hours. Okay, so what that means is we're going to be plugging in cubed. Okay, now if we're going to talk about how to put this on a calculator, okay, so bring this into play here. Oh, let me clear my screen. Okay, I can do, now, if you're on a grapher like this, okay, you're going to do 42.2, and then you're going to open that set of parentheses, open that set of parentheses, and then you're going to put in 1.56, and you're going to close your set of parentheses, okay, and let me get a little bit closer here. Whoop, there it is, okay. Now, what you're going to press is, you're going to press this little wedge or caret button, okay. And this is, now, on my calculator, okay, it goes ahead and it pushes it up into that exponent spot, okay. On some of the other calculators, okay, when this is put on, okay, when this is put into play, there we go. Sometimes it will just put this the little caret symbol, and then you're putting the number 3, okay. Now then, we get 160.2087 with a bunch of stuff, and it said to the nearest dollar, so we're going to do $160. Okay. Now then, if your calculator does not have the capabilities to do all of this, okay, what you would start with is this portion of it and get the 1.56 and raise it to the third power, and then you would multiply that with the 42.2, okay, and you would come out with the exact same response, okay, that we did. We're pretty close, okay, shouldn't be off by too much. Now, couple of examples that we look at, okay, so first off, we're going to look at 2 to the x. Now, taking a look at a table of values, okay, now then, 2 to the first is 2, 2 squared is 4, and 2 cubed is 8, okay. Now, 2 to the 0 is 1, and guys, this is because you need to remember that anything to the 0 power is 1, so long as a isn't 0, okay. This is one of those exponent rules that you just have to know, okay, or it's one of the exponent rules that it is just law. Now, let's talk about those negative exponents, okay. When you have something that is a negative exponent, it drops that into the denominator and it loses the negative. So this would be, so when we talk about 2 to the negative 1, that is 1 over 2 to the first, which is 1/2. 2 to the negative 2 would be 1 over 2 squared, which is going to be 1/4. And then we have 1/8, okay, for our table. Now, if we are going to graph, okay, we've got 3, 8, and 2, 4, and 1, 2, and 0, 1. And then here's where it gets a little bit harder to graph, okay. But what's going to happen here is our graph shape is going to look kind of like this. Now, a couple things to know here. One is, let me not do that green, let me do it a different color. We do have a horizontal asymptote sitting right along the x-axis, okay? And guys, if you think about it, each one of these is half of what it was before. So every time I cut a number in half, even though it's getting smaller, there is still stuff there, okay? No matter how many times I cut it in half, it's always going to have stuff there, okay? Now then, this is also the pattern, okay, for any okay? Exponential that has a base bigger than 1. So if this was a 3 or a 4 or a 5 or a 2.7 or anything like that, this is your basic shape, okay? It's going to be getting higher on that right-hand side, okay? So now, if we look at, okay, something like 1/2 to the x, okay? Hey, Chris, can you tone that down just a bit? Okay. Looking at our table, again, working off of those same ones. Okay, again, we know anything to the 0 power is 1. Anything to the first power is itself. When we square this, okay, okay. Now, looking at the negative side of this, okay, we talk about -1 to the -1/2. That is 1/1/2. Now, another way to look at this, okay, this big fraction bar right there, this can be written as a division symbol. And if you remember, when you divide by fractions, you switch it to multiplication and you flip it over. So that's going to be 2. Okay. If we do -2 up here, that's going to square this on the bottom. So this will be a 1/4. So you get 4 and you get 8. Okay. So going in and doing the graphing stuff for that. Okay. Here, 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 4.5 and 1/4. Very, very similar graph. It is in the same family, okay? And again, this is going to have a horizontal asymptote that sits right here along the x-axis as it sits there, okay? And again, this is a basic shaping for anything that has a base that's bigger than 0 but less than 1. So a lot of those fractiony type values that we have there, okay? And so we have, those are kind of our 2 basic exponential shapes that we're going to have, okay? So now, couple of characteristics, and I'm just going to pull the PowerPoint over here so that we can talk about this real quick. I'm going to bring this down. There we go. The domain is going to be all real numbers, and we saw that with the graph that it did go all the way from the left to the right. The range is going to be from 0 to infinity. Notice the parenthesis on the 0. Because 0 is not included. That's where that asymptote is. Every graph is going to pass through the point 0, 1. And again, there's that rule. They do b to the 0 equals 1. Okay. I did it as an a, but it's the same thing. If b is greater than 1, then the graph is increasing as it goes to the right. That's the first graph style that I showed you. If b is between 0 and 1, then the graph decreases as it goes to the right. That was the second graph type that I showed you. This is 1-to-1, and it has an inverse that is a function. I'm going to talk about that here in just a second. And then the graph approaches but never touches the x-axis, so it does have a horizontal asymptote of y equals 0. Now, coming back to this one on number 5, about it is a 1-to-1 function. What does it mean to be 1-to-1? Okay, a 1-to-1 function. Okay, first off, function is x's don't repeat. Okay, 1-to-1 says the y's don't repeat. Okay, so because it's a 1-to-1 function, it has both the x's and the y's don't repeat. Now, what this also ensures, if you remember back to when we talked about inverses, okay, back over in chapter 2, we talked about like a horizontal line test and that the y's don't repeat each other on those. That's what this creates. It says that not only are we going to have that this is a function, its inverse is also a function. So this would pass a horizontal line test. And if you go back and look at those graph pictures, you can see that sure enough, they do pass that horizontal line test, which means they have an inverse function, okay? Now, I'm going to pull, okay, and this would be a spot where you would probably want to go look at the PowerPoint, okay, so that you can get this next slide, okay? So this is how we do all of the graph movement stuff, okay? So if it is a plus or minus C back here at the back, this is your up and down stuff, okay? And it's going to do exactly what you think it's supposed to do. Now, horizontal shifts, okay, is going to be up in the X with the exponent. Now, sometimes they'll put this stuff in parentheses, sometimes they don't. If they don't, I usually do it because, again, they need to do the opposite of what we think it's supposed to do. Now, with the reflections, if the negative is out in front of the B, it flips over the x-axis. If the negative's up with the x, it flips over the y-axis. And I'm going to talk about that one with the negative out in front here in just a second. If it's a vertical stretch or shrink, it will do exactly what you think it's supposed to. If C is bigger than 1, it stretches it. If it's between 0 and 1, it's going to shrink it. The negative is dealt with separately if it's there, is out in the front, and then it's kind of hard to see, but it's CX up in the exponent, that is your horizontal. And again, because it's up in the exponent, it's going to do, and it will be with the X inside a set of parentheses, it's going to do the opposite of what you think it's supposed to do. Now, back to that one about the reflection, okay? I am a wee bit leery, okay, when they do something like this, because the question is, where does this negative go? Does the negative go with the 2, which is, we don't do those because that makes it a negative base, and that's not allowed, or does it go here, okay? And if they don't specify, it's kind of hard to tell. So, personally, what I do is if I want to do a reflection over the x-axis, okay, I'm going to put this part of it in a set of parentheses and then stick the negative out in front so that you know it is separated from the rest of that, okay? So if we want to talk about graphing stuff, so if we want to graph something like 3 to the x minus 1, okay? Now, first off, I'm going to stick a set of parentheses around that, okay? Just so that I remember what it does, and that is going to make it go right 1. Now, a couple of things that I do on my graph picture. First off, the points that I use on every graph, we already know are 0 and 1. We also have the point 1 base, okay? So the way that I go about doing my graph pictures is, number 1, I'm going to mark with a little X, 0, 1, and 1 base. And in this case, my base is 3. Okay, so I'll put these little X markers here. Now, for my graph, both of those points need to move to the right 1. So I'm going to take this X and I'm going to move it to the right 1. It's going to put it there. And then this point will also move to the right 1. Now, the other thing that has to move is the asymptote. Okay, so it's normally sitting right here along the x-axis. Move it right 1. It still stays right along the x-axis, so that asymptote is still there. And then we're going to connect the graph. A nice pretty point, okay? And what this allows me to do, okay, is it allows us to move graphs without having to try and find a bunch of ordered pairs. It also, you don't have to play guessing checks, okay? So I use these 2 points and my asymptote and I move stuff around. So for example, okay, kind of pulling another one here. And again, I'm going to keep my points here that I had. Let's say that I had 2 to the x plus 1 minus 1, okay? And again, first thing I'm going to do, set of parentheses around that. Now, that is x plus 1, so that is left 1, and this minus 1 is going to be down 1. So, going to my grid space, okay, 0, 1, and 1 base. My base is 2. So there's my 2 points that I'm going to use. Now moving these around, okay, each point needs to go left 1 and down 1. So I'm going to go left 1, down 1. It's going to put it here. Left 1, down 1 is going to put it there. And then my asymptote, okay, is going to be left 1, down 1. Now that's actually going to move that asymptote to here. Okay, so now when I play connect, there's what my graph is going to look like, okay? So hopefully you kind of get the idea of how that graphing goes with that. Now, the next thing is there was a Swiss, I'm pretty sure he was Swiss mathematician, okay, that what he was playing around with was 1 plus 1 over n to the n, okay? And so if we think about this, if I let n be 2, this would be 1 plus a half squared, and then 1 plus a third cubed, and 1 plus a fourth to the fourth, and so on and so forth. And what he realized is as n got really big, okay, this number started to turn into 2.718281827, okay? And the thing with this number is it doesn't repeat, okay? So it's not like I can do 71828. There's not a spot that I can go, oh, it repeats, because it doesn't ever repeat. Just about the time you think it does, it changes. Now, the math world took notice because this was a really good number. This helped a lot when we were doing things like talking about growth, population growths, and things like that when we were going through. Now, this number was given the value E, okay, and they named it after the guy. Now, everything in my East Texan makeup, okay, says that that is Euler. It is not. The guy's name is Euler, okay, like O-I-L-E-R. And so they named it after him when they did this, okay? So taking a look, now the other thing is that when you see, this is generally on a calculator, okay? They will have a lowercase e on your calculator someplace, okay? And so if you see them using this, that is the button that you need to use for this, okay? So taking a look at one of these in application, okay? We have the function, okay? And this is supposed to represent the gray wolf population in the Western Great Lakes in X years after 1978. And guys, you got to pay attention when they do stuff like this where they plug up and they say that X is going to be sometime after a particular year or something like that, okay? Because you're going to need to make sure that you figure out the difference. Now, they want to know what is the population or what was the estimated population in 2012. First off, I need to do 2012 minus 1978, and that's going to give me 34. This is my X value that I'm going to be plugging into this equation. So 1066 e to the 0.042 times 34, okay? Now, again with the calculator, and I'll show you how to do this here in just a second, okay? If you want to make life a little bit easier on yourself, okay, a lot of times with some of the other calculators, it's a little difficult to get this to all read as one thing. So it may be easier to go ahead and multiply that out and get 1.428. So all I did there is 0.042 times 34 and got this, okay? This now makes it a little bit easier to put onto a calculator. Now, if we're going to talk about where this is on a calculator, okay? So I'm going to turn my calculator on, okay? So I've got 1066, okay? Now, if you're on a grapher, this LN button, in blue, just above it, it says E to the X. Okay, let me zoom down here. Okay, here is my LN button, and you can see E to the X right above it. Okay, so it is in blue. Okay, or it's in an alternate color. For me, it's blue, so I'm going to press second, and then that button, and I'll zoom in on my screen here real quick. Sorry, guys, it's a little jostly. Okay, and I have E, and now it's sitting there waiting. Okay, now again, if your calculator was one of the ones earlier that it showed you the little carrot top wedge, it's now going to say E, and then it's just going to have that little carrot top wedge. And I'm going to put 1.428. Okay, and then I'm going to press enter. Now, here is the concern. I'm getting 4445.59. Y'all, I don't care if a wolf has lost a leg, okay? It does not get counted as a partial wolf, okay? So you need to make a decision, okay? And for this one, I would accept either 4445 or 4446, okay? I would take either one of those answers. For this one, kind of the decision is I have 445 whole ones, and then this extra one was just a, one that doesn't need to be counted, or we're going to go ahead and let it go up and say that I actually had that entire wolf when it went through. Now then, one of the things, if you remember, okay, back when we did composition, okay, back over in, I believe that was back over in chapter 2, composition, I told y'all the story about buying my truck, okay, and I talked about the, when we were doing the credit stuff, and I said that I was working stuff. Guys, this is when we're going to talk about that equation. So the equation for compound interest, okay, is A equals P and then 1 plus R over N to the NT. Now, A is the amount in the account. This is how much you're ending with. P is your principal, okay, which is your starting amount. R is your rate, and this needs to be in decimal form. N is the compoundings, okay? This is how often you are getting your interest, okay? Some accounts only do once a year, some accounts do it twice. It could be 4 times a year, things like that. And then T is time, and this is usually in years, okay? If they don't talk about it in years, you probably need to get it in years, okay? Now then, hopefully you kind of see this 1 plus, and we see this over N to the N. Kind of looks like Euler's thing that we had before, okay? Now, if you can get what's called continuous interest, okay, this formula morphs into A equals PE to the RT, okay? All the letters here are the same as the letters are up here, okay? They are just, it's a slightly done. Now, with the continuous interest, this is, you are getting interest non-stop, okay? It's not monthly, it's not daily, it's not by the hour, it's not by the minute, it's not even by the second, okay? It's even faster than that. It's just sitting there continually, constantly gaining interest on it, okay? The other times, like up here, what they do is they look at the amount in the account at the point in time where they're going to put interest on it, and then they lump it in there and they dump it off, and then they sit and wait until the next time that it happens, okay? So the example problem that we're going to look at for this is which is the better investment, okay? So we have $10,000 that we're going to invest, okay? And it's going to be in for 5 years, okay? Now, option A is we get 8% compounded quarterly, okay? Option B, okay, is we get 7.8% continuously, okay? So, there it goes, okay. So the question is, which one's better? Now, this is a situation where this one has a slightly higher percentage rate, but I'm not getting my compounding as often. This is slightly lower, but I'm getting it all the time, okay? So there is not a way to check, okay? Because it may be at 5 years, this one's better than that one, but at 10 years, they may flip-flop, okay? So it's not a, this one's always better than this one, or this one's always better than that one, okay? You just have to run the numbers. So let's take a look at option A. Okay, so for option A, we're going to do A equals $10,000. 1 plus, now 8% in decimal is 0.08. Quarterly means 4. And then 4, and our time was 5. Now, I am going to clean this up a little bit before I take it to a calculator. Okay, so I've got 10,000. 0.08 divided by 4 is 0.02. So I have 1.02. And then 4 times 5 is 20. Okay, so now pushing to a calculator. I've got 10,000, 1.02 raised to the 20. Now, guys, we are talking about money here. Okay, so it makes sense for me to go to 2 decimal places. Okay. So there is kind of the first option. So now looking at the second option, okay, now real quickly, this was A equals P1 plus R over N to the NT. That was my formula. And the formula that I'm using over here is the A equals P e to the RT. So we're going to have A equals, and again, 10,000 e to the 0.078 times 5. Okay. And again, I'm going to clean that up just a bit. That's going to be 0.39. So I've got 10,000. E to the 0.39. And I get 14,769.81. Okay. So at the 5-year mark, this one is my better investment. Now, that is not to say at 10 years, it would still be the better investment, okay? It may be that this one starts out kind of slow on the uptick, and then all of a sudden it goes really, really fast. And this one just kind of keeps plugging along. There is not a way to ever tell which one is going to be the better investment at any point in time, okay? So you just have to kind of plug and chug and move and process through. So now, the next thing that we're going to do is we're going to move into section 4.2. Okay. Section 4.2 is about log functions. Okay. Now then, okay. Now, basically what happened here is mathematicians wanted to be able to find an inverse function to the exponential, okay? And the concern was they took that y equals b to the x and they switched the x's and y's. And then they said we need to solve for y. They couldn't get y back by itself because you can't divide off the b because it's not multiplication, it's an exponent. You can't take a root because I don't know which root. It changes, okay? So I can't do a square root one time and a cube root the next time. So what they came up with was this. Now, one of the things that you've got to be able to do is you have to be able to switch back and forth between the two formats, okay? So I'm going to show you how to switch back and forth between the two styles. So if you are sitting in an exponential, or sorry, in a log format, okay? So if you're sitting in log and you need to move to exponential, okay? What you're going to do is you're going to use what I call an E-loop, okay, for exponential. So, and the way this works is you're going to start on the base, and you are going to loop through, okay, so it looks like a cursive letter E. And so you're going to write down the first thing that you were on, so in this case the 7. The second thing becomes the power, and then you put equals, and then you hit the last thing that you were on, okay? So looking at another one, okay, we've got log base b, 25 equals 2. Okay, so again, I'm going to loop. And I have b squared equals 25. Now, you may be starting to get the idea here, okay, that in its log format, okay, it is not very conducive to being able to solve, okay? However, okay, when I switch it over to its other format, okay, it becomes a little bit easier, guys. 7 cubed is not difficult to find. I can figure out what number squared gives me 25. This one might be a little more challenging, okay, but I can certainly kind of sort out what that is supposed to be, okay? And that is because our brains don't necessarily like to work in log, okay, but we do like to work in exponential. Now, the other thing is, though, that there are some things that we want to do in log, and we're going to see these over in section 4.3, that they are really, really pretty when they are over in their log format. In exponential, they're a lot more difficult to deal with, okay? So the concept is we need to be able to move back from this format back over to here, okay? And so we have another little shaper for this, okay? So I'm going to get rid of all this real quick, okay? And so we've got 2 to the 5th equals x, okay? Now, for this one, I want to go to log. So I'm going to use an L for log, okay? And it's going to be a capital L. And it's going to look like this, okay? So again, the way we're going to start this, we're going to start with the word log. The first thing we hit is our base, okay? And this is subscripted, okay? It is written little bitty and a little bit lower, okay? Then we're going to take the second thing, which is an x. Then we're going to put equals and then the last thing, okay? So let's take a look at another one of these. So I've got b cubed equals 27. So I've got log base b, 27 equals 3. And e to the y equals 33. So I have log base e of 33 equals y. Now, this we're going to see written differently a little bit later. Okay, so we'll wrap back to that. Let me write that a little bit better. Okay, this log base e gets written a little bit differently, but for right now, you're just being able to transfer between the two. Okay, so now one of the things that we can start to do from here is we can actually try to solve a couple of these things. Okay, so for example, if I have log base 10 of 100 equals x, okay, actually, okay, they will hand you the problem just like this. First thing I'm going to do is I'm going to make it equal x so that then I can do my stuff. Now, this is in log, so I'm going to do my little e loop. So now I have 10 to the x equals 100. Guys, 10 to the what equals 100? X has to be 2. So there's my answer. Okay. Now then, next one. Okay. So I've got log base 5 of 1 over 125. Again, I'm going to say that it equals x just so that I have all my parts and pieces so that I can e-loop. Okay. So now I've got 5 to the x equals 1 over 125. Now, guys, thinking back to the last section that we just did, in order to get this to go underneath the exponent, it's going to have to be a negative. If this power is negative, it's going to drop it under. So now 5 to the what power gives me 125. So 5 squared is 25, and then times 5 is 125. So that's going to be 3. So x is going to be negative 3. Okay? So So now I've got log base 36 of 6. And again, I'm going to put that it equals x, just so that I've got all my parts and pieces. Okay, now with this one, guys, you are trying to take a base that is bigger down to one that is smaller, but it's not in a fraction. Okay, so it's not like a 1 over, so this is not going to be an exponent. If we think about this, the square root of 36 is 6, okay? And the way that we do this, okay, is square root is the same thing as an exponent of 1/2, okay? So x is going to be 1/2 in this case. So if you need to do a square root of a base to get to an answer, then that exponent is 1/2 for that. Okay? That one is a little bit different. We will see a couple of other ways to do those problems a little bit later as we process through the example, okay? Now, a couple of things of note here, okay? Log base b of b is 1. Guys, basically what this is, and if you loop this out, okay, you get b to the 1 equals b, which is certainly the case. Okay, we have log base b of 1 is 0, and that is because b to the 0 equals 1. Again, watching that loop out. Okay. Okay. Now, the other thing with this is basically they took rules over here that we knew and they wrote them in log form. Okay. So two others that we have: log base b of b to the x equals x, and this is because b to the x equals b to the x. And then a reverse form of this, and we'll see these two come into play a little bit later as we move forward. So for right now, though, we kind of deal with these other two, okay? Now then, if you remember back, okay, and it wasn't too long ago, it was section 4.1, we had a graph that looked like this, okay? And the table for this, and I'm going to do an abbreviated table. Okay, this was 1/4, 1/2, 1, 2, and 4. Okay, the inverse, okay, which is log, okay, is going to be 1/4, 1/2, 1, 2, and 4, -2, -1, 0, 1, and 2. Guys, the x's and y's are flip-flopped into this, okay? So when we look at this graph, this graph looks like this. And this does have, instead of having a horizontal asymptote, this one has a vertical asymptote, okay? And this is log base 2 of x, okay? This is the graph for log base 2 of x, okay? Okay. Now then, for our 1/2 to the x, again, abbreviate, and if the table or if the graph you remember, the graph went this way, okay? So table, this was 4, 2, 1, 1/2, 1/4. So when we do the inverse of that, okay, so if we go over here, here, Okay, this graph is going to go this way. It also has a vertical asymptote that sits right along the y-axis. This would be log base 1/2 of x. Okay. Now then, one of the other things that we discussed about inverses, okay, is that they reflect across the line y equals x, okay? And so one of the things that's going to come about, and I'm going to show this one on the PowerPoint slide. I'm going to bring this up real quick. Okay. Is it's easier, it's slightly easier to see here. Okay. This is the graph of 2 to the x, and then this is the graph of log base 2 to the x, and you can see them as they go across that diagonal line, y equals x. The other one is a little bit more difficult to see. This one here, this first one that's kind of over here in quadrant 2, that is your 1/2 to the x, and then this one that's kind of down over here in quad 4 coming upwards, that is your log base 1/2. Okay. This one's always a little more difficult for me to see just because it crosses over that diagonal line. And so it's just a little more challenging, I think, for me to see. Now, a couple things I'm going to slide up into this next set where we're talking about the characteristics, okay? The domain for this is going to be from 0 to infinity. Let me see if I can get this to focus a little better for me, okay? And the range is all real numbers. This is the exact switch of the domain and the range from an exponential function, okay? All the graphs are going to pass through the point 1, 0. And this is because log base b of 1 is 0. Guys, that's also the reverse of the point 0, 1 that was on the exponential one before. Now, these two next two are the same. If b is greater than 1, then it increases as you go to the right. If that base is between 0 and 1, it's going to decrease as it goes to the right. And then this one, the graph approaches but never touches the y-axis, so it has a vertical asymptote at x equals 0. Now, the last time we had a set of these, there were 6, and it talked about the inverse function. We do not talk about inverses of inverses because that sends us back. Now, the other thing here is our lovely little transformations. Okay, let me get this lined up nice and pretty. Now, the good news about the transformations part for this, okay, is if they want parentheses, they're going to put them, okay? Let me get this to focus up a little bit better, okay? So if they want it to be a horizontal shift, they're going to put it in a set of parentheses, and it is going to go the opposite of what you think it's supposed to. If they don't want it to be a horizontal shift, if they just want it to be a vertical, then they're going to put it out there at the back end, and they are not going to put parentheses around it. So do not go adding parentheses on this, okay? Now, with reflections, okay, we have a negative out in the front, still flips it over the x-axis. On the inside, guys, it's like math commandment. Thou shalt not take the log of a negative number, okay? Now, with that being a negative x on the inside, that makes it a little funky, okay? So we do have to watch that kind of stuff. Again, vertical stretches are done out in the front end. Horizontal stretches and shrinks are done on the inside, okay? So I'm going to bring this back up. There we go. Okay. So now, talking about an example of graphing one of these. Now, key points, okay, talking about points for graphing. I'm going to be using the point 1, 0, okay? And I'm going to be using the point base 1. Okay, these are the flips of the 2 points that I used to use when I did the other ones. I'm also going to use, I'm going to be using that vertical asymptote that sits along the x-axis. So, taking a look. They had this in a set of parentheses, which means this goes right 5. Okay, so here we go onto our grid space. First off, I'm going to put the spot here at 1, 0. My base is 4. So 1, 2, 3, 4, and 1. So I'm going to use those 2 points. Okay. Now, I'm going to get ready to start moving my points right 5. So I'm going to add several more spots out here. Okay, so this point is going to go right 5. So 1, 2, 3, 4, 5 is going to put it right there. This point is going to go 1, 2, 3, 4, 5 right here. Now, we have that asymptote sitting here on the or on the y-axis. So 1, 2, 3, 4, 5 is going to put that vertical asymptote right here. Okay, so now I know to stay off of that. And we're going to arch up and come back down. So there is our graph picture for that lovely graph. Okay, so again, I'm only moving a couple of points and an asymptote to help me get my graph shape for where that needs to go. Okay, so clear this. Okay, now with logs, there are a couple of bases that are special. Okay, first one that we talk about is common log. Common log has a base of 10. Okay, and we do not write log base 10. This is, if they don't put a base, it is an automatic understood 10. So if they don't put one here, now guys, when you look at your calculator and you see the log button, that's the one, okay? The log button on your calculator is log base 10, okay, for that one. Now, the other one is natural log. Natural log has a base of E, that Euler's number, okay? And I showed you earlier that we had like log base E of Y. We don't write this, okay? This is LN. Sometimes they'll do this in capitals, okay? You're going to see me write it in script, okay? I'm going to write LN. Now, for the love of all things math, okay? On Math Lab, please, 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 the biggest thing that I see done wrong is people put 1 in, okay? Because that is L, okay? This is the lowercase l, but it is not the number 1, okay? So this is not 1 in, okay? I have seen students mess this up where they will get frustrated because they are not paying attention that should be LN for natural log. Now, if you're wondering why is it LN and not NL, okay? You got to realize most of our math stuff came from Europe, and in a lot of those languages, the describer, the adjectives, come after the noun, okay? Taking Spanish, myself, I remember talking about like the black dog was perro negro, okay, where the describing the color came after the word dog, okay? So if we think about it in that terms, logarithm natural, okay, or log natural, which would be the kind of roughed out translation of it, would have been translated as LN, not NL, okay? So please do be mindful of that as we process through, okay? Now, one of the things that came about, and I'm going to, again, just kind of zoom down here on this real quick, okay? These are the properties that we had before. Here are the first 4, okay? And what I did is I put them in common log, and I put them in natural log. And again, that is LN for that, okay? Now, we will be using these properties a little bit more as we process through the rest of this chapter, okay? But this is a nice, pretty chart that puts it all together. I think the book took a couple, 3 pages to try and put all this stuff together. I'm not quite sure why, okay? But there it is in a nice, pretty chart, okay? So moving forward, okay, towards a couple of others, okay? So we have, for an example problem, okay, we have f of x equals 29 plus 48.8 log x plus 1. Notice they did not put a base on here, so it is automatically base 10. This is also the log button that is on your calculator. Now, it says this represents, x is the boy's age between 5 and 15, and f of x represents the percentage of his height, of his adult height, okay? So it asks, at age 10, approximately what percentage of his height has it had. So we're going to do 29 plus 48.8 log 10 plus 1. Okay. Now, with this, okay, going to our calculator. Excuse me. Most calculators, when you press log, they automatically open a set of parentheses for you, okay? Make sure that you are closing that set of parentheses when you are done with the log command. Okay, so we're going to let this go. And we get 79.82 is what I'm going to call it. And again, that was a percentage. So we have that. Okay. Hopefully everybody's good with all of that. Okay. So now then, moving on to section 4.3. This is the last section that we're going to have to cover for this evening's session. Okay. And this is properties of logs. This section is the shortest, okay, of the three that we're having to cover tonight. And these are some properties that we are going to be making use of as we process forward going into Wednesday night session over solving logs, okay? So we have three properties that we're going to be looking at. We have what's called the product rule. And this says if log base b of mn can be separated into log base b of m plus log base b of n. Okay. We have the quotient rule. And it says log base b of m over n. And the PowerPoint does not have it written in that nice pretty fraction like that. It does it with the slashed division symbol. Okay. Okay. And then we have the power rule, which says log base b of m with a power. This power can come right down out in front as a multiplier, okay? And normally we won't see this multiplication dot because it's actually just a number, okay? So what we want to look at is there are kind of two things that we're going to do. The first thing that we're going to do is expand, okay? And guys, if you think about anything that expands, it gets bigger, okay? So we're going to look at a couple of different rules here, okay? Each one of these in application, okay? So we're going to start with log base 6 of 7 times 11, okay? And so we can separate this to log base 6 of 7 plus log base 6 of 11. Okay, and that's done. Okay, that is as good as that gets. Okay, and that is it can't go any farther. Okay, so now looking at another one, we've got log of 100 times x. So this is going to be log of 100 plus log of x. Okay, now here's the deal though, guys, because this is a base of 10, we can do this. So because 100 does go through. Now you can put log of 100 on a calculator and you're going to get 2 for that answer. And then we're still going to have that log x at the back. So that is kind of where we see that done. Okay, so just kind of taking that in general setup for what's going on there. Okay, so now looking at a couple more, we've got log base 8 of 23 over x. So this is a quotient rule. So we do log on the top minus log on the bottom. Okay, and that is as good as that gets. It won't go anywhere else. So now another one. Natural log of e to the 5th over 11. Okay, and again, I said I write mine in script just so that there is no confusion over what that is. Now, again, knowing that natural log has a base of e against this, what's going to happen is this actually turns into, sorry, not equals, correct? Okay, that's going to turn it. And guys, this is using that property out of that table that was at the end of section 4.2, okay, for that one. Okay, so there's a couple of quotient rules. And now power rules. Okay, that's a 9. So for this one, the 9 is going to come out in front. Okay, and that's as good as that gets. For this one, okay, I talked about that square root was a power of 1/2. Cube root is a power of 1/3, and you are expected to convert roots to powers, especially if they're sitting in log notation. So this is going to be 1/3 natural log of x for that one. Okay. And then one more for this one. If we have log of x plus 4 squared, the 2 will come out in front, but you do need to keep this x plus 4 together. We do not have rules that separate log on addition. It's only when the inside is multiplied or divided that we are allowed to separate those out. Okay, so hopefully that kind of gets to the basics. Now, what happens when they try to put all of it together? Okay, now the general order, this is just the general order when we're expanding. Okay, there will always be, you know, 1 or 2 exceptions to the rule, but when we're expanding, the first thing we want to do is we want to do quotients. The second thing we want to do is products. And the last thing we want to do is powers. Okay, so that's kind of the order that we follow. So I'm going to do a couple of these and we will kind of separate and expand them as we process through. Okay, now certainly if I don't have one of these, I kind of keep moving down into the next thing that's there. So okay, so here is the one that I'm going to start with. So the first thing is quotient. I don't have any fractions over here, so I don't have to do that one. Next thing is product. I do have 2 things in here, so I can separate this x to the 4th plus log base b cube root of y. Okay. Now going into this next step, I do want to take this cube root and turn it into a 1/3 power. Okay, and now I can bring my powers down out in front. Okay, and there is my final equation for that one. Okay. Okay. So looking at another one, so we kind of get one that does have kind of all of the stuff in it. I've got log base 5 of square root of x over 25y cubed. Okay. So first thing here is I do have a fraction. So we're going to separate the top from the bottom. Okay. Now the next thing is I don't have any product over here, but I do have a product over here. Now we do need to be careful, okay, because when I have this subtract, everything that I'm fixing to do here needs to stay subtracted. Okay, So I want to make sure that all of this second part stays subtracted, okay? So I put it in a big set of blocks here, okay? Now, the next thing that I'm going to do is I'm going to switch this 1/2 up, or this square root up to a 1/2 power. And then I'm going to bring my powers down out in front. Now, the other thing here is, guys, log base 5 of 25. Because this matches, this is actually the number 2. Okay. Okay. And they may leave it just like this. The other way, kind of an alternate way that you may see this done, is they may go ahead and distribute. Oops, sorry. Okay, is they could go ahead and distribute that negative out through the line when they're doing that, okay? Now then, if they ask you to expand, the logic follows that they could ask you to shrink them back up, okay? That process is called condensing, okay? And basically we do everything in reverse, okay? So when we're condensing, okay, we do powers first. So we're going to take powers and push them back up. So if they were in front, they're going to go back up. Then we're going to look at products to bring back together. And last thing is quotients, okay? And that's because we only want to have one fraction in here. Now, when you're doing this, past moving powers back up. As you process through the rest of this, you should have less log words in each line that you are doing, okay? So, for example, okay, if I have log of 25 plus log 4, okay, I don't have any powers, but I do have a product. Add goes back to multiply. So this is going to go to log 25 times 4. That is log of 100, which actually has an answer of 2. Okay. And again, at this point, there wasn't anything that I could do to clean that loveliness up, but after condensing them and combining them, I can actually get down to a nice, pretty answer, okay? Now, looking at one that may not have or come down as well, okay? We're going to do log of okay. This is a pretty straightforward one. I don't have any powers in front. This add is on the inside of a log, so it is not a product rule, okay? And the only thing I actually have here is the subtract. So this is going to go to 7x plus 6 over x. And that's as good as that is going to get. Now, for one that is a little more involved, okay. So first thing is powers, okay? So we're going to take this 2 and we're going to send it back up. And we're going to take the 1/3 and also send it back up. Okay. Now I have add. Again, this is inside, so this is not a product rule. So we're going to combine these two. So I have natural log of x squared and then x plus 5 to the 1/3. Now, the other thing is with this 1/3, they could very well expect you to make that back into a cube root of x plus 5. Okay. That could be anticipated, and they could do that, okay? That this 1/3 power is pushed back down into a cube root, okay? Now, the last thing, okay, that we're going to do, okay, is what's called change of base. Now, the reason that we use change of base is our calculators can only really function in 2 bases. They can do common log, which is base 10, and they can do natural log, which is base e, okay? So what we do is this allows us to do any other log base. So log base 2, log base 7, log base 12, any of the other ones, and I can use my calculator to help me do this, okay? So the general rule is log base B of M is log base A of M over log base A of B, okay? B is the base that I don't like, A is the base that I do like. So what we more often see this as is we will go over to common log or natural log, okay? So we will either use common log here or natural log when we're processing through here, okay? So taking a look at an example, if I want to do something like log base 7 of 2506, okay? If I were to do this in common log, I would have log 2506 divided by log 7, okay? Now, moving into a calculator for this, okay? Now, this is where closing your parentheses is super duper duper important. So I'm going to press the log button, and I'm going to put in 2506, and I'm going to close that set of parentheses. And then I'm going to hit divide, and I'm going to do log 7, and I'm going to close that set of parentheses. I'll bring this down so you can see this, okay? Make sure that you close that set of parentheses after that 2506 before you go into the next part of this, okay? And when I press enter, I get the answer 4.021996, and there's a bunch of stuff after it, okay? Now, you can also do this same thing, okay, in natural log of 2506 over natural log of 7, okay? And same game, okay, and I'm going to do this a little bit closer so that you can see. So I'm going to hit natural log 2506, and I'm going to close that set of parentheses, divided by natural log of 7, and again, I'm going to close that set of parentheses. And guys, notice I get the exact same answer, okay? It is the exact same answer because we're still just looking for log base 7 of 2506, okay? So we anticipate that we should get the same answer. So that is the end of section 4.3, okay? I hope that you guys are kind of able to follow along as we're processing through here. And are kind of able to do stuff. Again, if you have any questions, please feel free to email me and ask me anything, or to ask my instructors. I'll be more than happy to help as best I can. So I will talk to you guys later.